Hi everyone, I am Dr. Kiran, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. So today we are discussing about capacitive filter. So overview of that today's presentation: filters, capacitive filter, and conclude with summary. So let us see what is the filter concept. So the rectified output of any rectifier circuit is not pure DC, it is a pulsating DC. That means it contains both AC component as well as DC component. In order to reduce the AC component in the rectified output, we need to minimize the ripples. Content of AC means ripples. So this is, we don't require this kind of ripples. Any DC device works on DC supply only. So therefore, the rectified output of any rectifier circuit have these ripples. So to minimize these ripples in the rectified output, we require a filter circuit. And why we need to reduce this ripples are varying with the time. So this kind of signals cannot be applied to DC or electronic devices. So this is an AC signal. So we should reduce this kind of ripples, unwanted signal, you can say. So filter circuit has components that have low impedance and high impedance. That means capacitive, inductor. So these are the two components having different impedances. So here, if you observe here, this is the rectified output of a full wave rectifier. So this is called pulsating DC. This is not pure DC, pulsating DC. But we require pure DC. So in order to reduce these pulses, we require some kind of filter. It may be capacitive filter or inductive filter. So the rectified output of a full wave rectifier is applied to a filter, and then it filters out the actual AC component in the rectified output. So then this is called VDC, that is voltage, DC voltage value. That means the AC component is reduced. So this is the overview of the filter circuit. So let us see one by one. Capacitive filter, it's very simple and inexpensive filter for very light loads. So what is the basic property of any capacitor? It allows AC component and blocks DC component. Okay, so we have AC represented with this signal, and DC component means, so which does not vary with time. So this is constant. Okay, so it allows the capacitor, the basic property of capacitor is to allow AC component and blocks DC component. Okay, and it operation is, the basic operation of this capacitor filter is to short ripple to the ground but leave the DC appear at the output. So here you will get the pure DC, or you can say ripple free output, ripple free DC component. So this is your rectified output applied to a, this is your filter circuit, capacitor filter. So capacitor filter, the capacitor component connected across the load resistor. Okay, so what is the basic operation? Let us see. So during positive half cycle of the input signal. So what is the input signal here? So this is your input signal. So this is positive half cycle and then negative half cycle. This is the actual output of the filter. Actual output of the rectifier, full wave rectifier. So this is applied here. Okay, and during that positive half cycle, so what happens? The capacitor charges up to peak value. Peak value means this will be the peak value Vm. So up to this point, the capacitor charges until, so it drops to 0, the input drops to 0. Input drops to 0, the capacitor charges up to maximum value of the input. And then during negative half cycle, the capacitor will discharge through RL, load resistor. This capacitor charges in the first case. The second case, the capacitor charges discharging through RL. So in such case, what happened? Until transformer secondary voltage again increases to greater than the capacitor voltage. So the voltage across the capacitor must exceed again, and it has then only the capacitor charges start charging. So the diode conducts for a period that depends on the capacitor voltage. So this is very important. Capacitor voltage means here diode voltage itself. So diode voltage, or you can say load voltage across the load resistor. What will be the voltage? That will be the capacitor voltage. So the diode conducts for a period depends on the capacitor voltage, that is load voltage. And the diode will conduct when the transformer secondary voltage becomes more than the cut-in voltage. So here, depending upon the different semiconducting materials, so we have cut-in voltage of the diode. Okay. So for example, if you take silicon, 0.7 volts is the cut-in voltage. For germanium, it is approximately 0.3 volts. Okay. So the diode will starts conductor. So depending upon the semiconductor which we have used, so based on that, the diode will conduct when the transformer secondary voltage becomes more than the cut-in voltage of the diode. So that means, so from this point, it will again starts conducting. Okay. But the basic property of capacitor, so during negative half cycle, so what happened? The capacitor discharges slowly. The capacitor discharges slowly until it starts completing one complete cycle. Okay. So from this point again, the capacitor starts charging like this. So due to the discharging time of the capacitor, it looks like, that means the ripples in the rectified output will be reduced. So here, this is the rectified or filtered output. Okay. So this is the time T2 for the time taken for the discharge. So this is time T1 for the charging purpose. The time required by the capacitor to charge is represented by T1, time T1. Then discharge time is T2. So if you observe this T1, T2, discharge time is more and charging time is less. Okay. So, and now let us see how we can, so the charge acquired by the capacitor and the charge lost by the capacitor is equal. See here, the charge acquired by the capacitor is given by, so we can say, we know that capacitor C is equal to, charge Q is equal to CV, capacity into voltage. So here what will be the voltage? VR, peak to peak voltage, into capacitor. Similarly, the capacitor loss is IDC, the DC current into time T2, because we know Q is equal to IT. So at some T2 time, what will be the current flowing to the circuit? Therefore, if you equate these two, so what we will get? So T2 will be T by 2, half of the time period. And then we can write, we know T is 1 by F, inversely related, frequency and time. So 1 by 2F. So then VR peak to peak is equals to IDC by 2FC. So the ripple waveform will be triangular in nature. So if you observe the signal, the ripples are triangular in nature. So this is your capacitor charging time and this is discharging time. Charging time and discharging time. This is discharging time. Okay. So if you equate these two times, so if you observe this look like a triangular waveform. So the nature of the triangular waveform, if you observe, the RMS value of the ripple is given by Vrms is equals to Vr peak to peak upon 2 root 3. So this is standard form for a rectangular waveform. So therefore, the above equation, so by taking the different assumptions, we can write Vrms is equals to IDC upon 4 root 3 because it is IDC by 2FC. So IDC by 4 root 3 into F into C. So that we can write VDC by, because we know IDC is equals to VDC by RL. So with that we can write VDC is equal to 4 root 3 F into C RL. So therefore the ripple factor, which is Vrms upon VDC. So this is root mean square. So this is the AC value of the RMS component. AC component present in the rectified output or filtered output here by VDC. Here 1 upon 4 root 3 F into C into RL. So the ripples may be decreased by increasing capacitor value, or you can RL value, or both. So if you decrease the value of capacitor or load resistor, then you can get the decrease in the ripple. So therefore we have to change the values of capacitor and load resistor to improve the effect of ripples, to reduce the ripples in the output waveform. Okay, so let us see one of the important basic property of capacitor is to the discharging time is more compared to the charging time. So based on this, let us see one basic example on this capacitance. So calculate the value of capacitance to use in a capacitor filter connected to a full wave rectifier operating at a standard aircraft power frequency of 400 Hz. If the ripple factor is 10% for a load of 500 volts. So we are given ripple the frequency of the full wave rectifier which is operating at 400 Hz. Frequency is given. Given data frequency is given 400 Hz. And what else given? Ripple factor is given. So ripple factor is 10%. So that can be written as 0.01. And for a load voltage is given 500 volts. So what is the expression for this, formula for this? 1 upon 4 root 3 into F into C into RL. So this is the expression just now we have derived. So if you we know values of all these. We know F is there and RL is there and then ripple factor is there. So only thing is we need to calculate C. So directly you can keep this C left side. Then we can write 1 upon 4 root 3 into F into rho into. So if you substitute these values, so what is C?